Oh, perfect. All right. Hello everyone. My name is Wojciech Różowski, as I was probably introduced, but I couldn't hear. I'm a PhD candidate at University College London, where I'm supervised by Alexandra Silva, and normally I'm working more on the theory side of programming languages and their semantics. And today, um, I would like to talk about the joint work I've done with my colleague Stefan Zetzsche, who previously was a PhD student in the research group where I am currently at. And the reason of this talk is not to scare you with a bit of formalism, but rather to show that you can formalize fairly complicated results using quite interesting Dafny features. The talk focuses on a classic result from automata theory in the semantics of regular expressions, namely that the 2 points of view at regular expressions match, and we rely on the support for coinduction in Dafny, which allowed us to construct these proofs. And this is based on the paper that Stefan recently presented and was recently accepted to ICTAC conference. All right, so without further ado, let's just get started. So regular expressions, whose syntax you can see at the bottom of the slide, are a formal syntax for specifying languages, and languages are simply sets of words, where words are sequences of letters taken from some alphabet. So, for example, 0 represents the empty language, so an empty set, or for every letter, there is a singleton set containing that letter. We can combine them using the union of languages, or compose them sequentially, or form a Kleene star. So from your from the introductory automata theory or theory of computation module at your university, you can go about semantics of these things in two different ways. So first of all, you can look at this compositionally. So the syntax of regular expression is something you can define via induction, and if you're able to interpret each of the operations, such as interpret plus as some operation on the set of formal languages, namely in this case it's union, or for example this dot to interpret it as a concatenation of languages, then by induction you can interpret every regular expression, and essentially that means that it's some sort of a compositional or algebraic point of view at this problem. And if you fix those interpretations, there is only one way you can do so in a well-behaved way. Alternatively, you can do it via automata theory, so we can construct automaton representing that regular expression, and to every automaton, you can uniquely assign a language each state accepts, and this automata theoretic point of view gives some sort of the alternative structure where the set of languages is equipped with a automaton operating on a set of all formal languages, and somehow map assigning the language to the states is also well behaved and preserves the automata theoretic structure. So we have those two ways, one at the top, which is this compositional algebraic, and one at the bottom, which is this automata theoretic one. So the obvious question is, are these guys well defined? Are those well-behaved maps, which are called homomorphisms, match? Is the map arising from automata theory preserving this compositional inductive point of view, and vice versa? Are these things equal? So this result, namely that these two, since I'm asking these questions, the answer is yes. And in this paper, in our work, we encode these 2 point of views at the semantics of regular expressions in Dafny and show that they are equivalent. So let's dive in. So in Dafny, you can very easily define the syntax of regular expressions as an inductive data type. So you define all the constructors corresponding to all the ways you can build a regular expression, and intuitively, the set exp is the smallest structure that is closed under those constructors. And this is like an inductive or algebraic point of view. And people call this initial algebra for the signature representing regular expressions. On the other hand, normally we view formal languages as just the sets of words, but we can look at them extrinsically, namely as the biggest structure where you can test for the empty word and check for cutting the prefixes. So essentially, the greatest structure that is equipped with a deterministic automaton structure. And this is something that arises through the dual of induction, where previously we talked about the smallest one, here we talk about the greatest one. Namely, it is something that arises through coinduction, or more, it's something in the semantics community is called final coalgebra. And those, again, excuse the formal terminology, but the point is that you can formalize in a pretty straightforward way these things using Dafny'. So let's dive in and let's go at the first point of view. So this compositional / algebraic one. So this is the textbook definition. This is how you would go and take the set of formal languages and equip it with all the operations corresponding to the signature of a regular expression. So again, you identify the 0 as the empty set, you identify 1 as the set containing the empty word, you interpret the plus as the union, the Kleene star as the Kleene star, and so on. And this is how you would do this if you just view the set of formal languages in this the set of words point of view. However, if you do this extrinsically via coinduction, you can define it using those observations you can make on the coinductive type, because while in the inductive point of view you can think of the different parts of the definition as constructors, those things in the coinductive point of view become some sort of a destructors, where you can check or make some observations of some potentially infinite data structure. And essentially, this is how you define all those operations on the set of formal languages by combining these observations. So for example, an empty language is the one that if you check it for the empty word, it does not have it. And if you try to cut any letter, you cannot do this. Or for example, the singleton language is the one that if you try to check for the empty word, it does not have it. And if you try to cut the letter that corresponds to the one you put in that set, then yeah, it's there. So this point of view gives rise to something that people call denotational semantics, or like compositional semantics. And the idea is that through the induction on the structure of regular expressions, you can just take, and every time you see an operation, you just use its interpretation on we just defined. And this thing preserves the algebraic structure, namely you interpret plus on the syntax side as the union on the semantics side, and so on. And this is something that is called algebra homomorphism. And in this talk and in this paper we've been presenting, we deal with looking at equality of things. And since we are talking about equality of coinductively defined things, let me mention the following subtlety. So you probably know about issues with extensionality of equality in Dafny', because it's not extensional. And when you try to compare two coinductive types, there is a canonical notion of their equivalence, namely bisimilarity. And it works that you can compare two potentially infinite things if you can make consistent observations between them, and they are in some sort of a lockstep. And of course, on paper, bisimilarity of languages and their actual equality is the same thing, but to go from bisimilarity to actual equality, you rely on functional extensionality, which is just not supported in the meta theory of Dafny' in the current form, as I understand. So we'll just work up to bisimilarity. But again, this is a very technical remark. But you can show that up to equality, this coinductive notion of equality, this inductively defined map nicely preserves the algebraic structure that is there. Now let's go at the dual point of view. So we went through the algebra point of view. Now let's go into the one through automata. So you can build an automaton whose state space are formal, are regular expressions. And to get a meaning of a particular expression, you will just look at the language corresponding to the state corresponding to that expression, and it's somehow defined similarly to the one operating on the set of languages. You just say how you would observe the empty word and how you would cut the letter from each of the regular expressions and to what regular expression would go to. So this gives you the output and the transitions map of the automaton. And you can take this automaton and embed it, take it to the world of formal languages and take something that behaves the same way. And this essentially is the map that takes the states of automaton to the corresponding language. And this we'll see in a second, is a well-behaved map that preserves automata transitions, namely is an automaton homomorphism, or again, speaking more abstractly, is something called Coalgebra homomorphism. Again, it's well-behaved up to bisimilarity. So now let's get to the main point, which is the well-behaved semantics. So showing that these two very different points of view are actually the same, they're equivalent. So that combining like compositional point of view and the automata theoretic point of view are consistent. So this is our strategy. Essentially, the well-behaved maps on which preserve the algebraic structure defined on the set of regular expressions are unique, and same with maps that take each automaton to a corresponding language. They are also unique, if up to bisimilarity. So we will show that the algebraic point of view also nicely preserves automata theoretic transitions, and these guys are unique up to bisimilarity. So it must correspond to the one arising as the one taking automaton to its language. So they are equal up to bisimilarity. And you can flip the picture and do the same thing and show that the map arising through automata theory also nicely interacts with the algebraic structure. And I won't go into detail, but the main point is that the fact that the denotational semantics also preserve automata theoretic structures relies on the fact that bisimilarity is reflexive relation, and it's compositional with respect to the syntax of regular expressions. And the fact that bisimilarity is reflexive actually gets automatically solved by Dafny' without any hints. So I would say this is quite impressive. You don't even have to hint these things. The fact that those well-structured automata maps are unique up to pointwise bisimilarity relies on transitivity of bisimilarity, and it's again a fairly straightforward proof. And the flip point of view that operate like semantics arising through automata theory works well with this compositional point of view relies on the symmetry of bisimilarity and its compositionality with respect to the star operation. So let me just wrap it up by talking about some related and future work. So we took this idea of building an automaton whose states are regular expressions circles back to Różowski in the 60s. This idea that the nice semantics are the ones which have both compositional point of view, but also some sort of an operational point of view given through automata or automata-like objects that interact the right way, have been introduced in the late 90s by Turi and Plotkin in the framework of mathematical operational semantics. And they introduced something called lambda bialgebra that was picked up later by Jacobs, who wrote a very nice review paper. That was a starting point for us. And in the context of theorem provers, Tritiel also very similarly to us looked at this extrinsic coinductive point of view at the sets of formal languages. But the different thing we've done compared to them is the fact that we actually gave this well-behavedness result. Regular expressions are quite of a simple language, but you can extend it to some more useful languages for equivalence-based verification, such as Kleene algebra with tests, which allows you to reason about programs with contour flow, with a Boolean contour flow, which has a very nicely decidable fragment, which allows to talk about the programs with while loops and if-then else's. And there is an extension for reasoning about packet passing software-defined networks, and this coinductive point of view there is actually very useful for efficient proof. So, long story short, we took quite of a nice and classic pen and paper proof that relies on a not so obvious theory and formalized it using Dafny', which has a very nice support for coinduction, and it allowed us to go from formalize those abstract theorems in a quite neat way. So with that, I would be more than happy to answer any questions you guys might have, and thank you very much for having me.
Are there questions?
Hi, nice talk. I wanted to ask you if you have considered the full expressiveness of regular expressions. I mean, the way Różowski introduced them in '64, including intersection and complement. That would be the first question. And the second question would be, have you thought about encoding things that involve very large alphabets, like infinite alphabets, where you need to take a more symbolic approach, as is done, for example, with symbolic automata?
Both, I would say both are really nice ideas. So I presume to answer the first bit, any derivative-based some sort of automata theoretic structure is something you could go and define and try to give a similar well-behavedness result. I think it would be very interesting. As for the latter one with infinite alphabets, that could be very interesting path of the future work, because as you mentioned, symbolic stuff or nominal stuff are incredibly useful, and the tooling support can be tricky for them. I'm only aware of this functional programming language called nlambda, which had some sort of a support for nominal things that also relied on SMT solving. So I guess it will be a very cool avenue for future work. And thank you for the recommendation.
Yeah, thanks. I have a third question and the third suggestion, which is to look at use of regular expressions as a search mechanism rather than a Boolean condition evaluation. Essentially, what I mean is looking at regular expressions with lookarounds, which can be defined with the span-based semantics rather than sort of language semantics on words. I think it would be interesting to know if your approach can also be generalized to this world.
So in that context, I was only aware of the formalization of the extended regular expressions in Lean. I don't know if these, so there was a work presented last year at, I think, Tidy workshop that talked about this, but I think they only had one side of the coin, like this derivative-based approach, but I'm not sure. But I know that people are interested in these. So yes, it would be also a very interesting avenue for the future work.
So there is a work last year at CPP'24 that you could take a look at.
Oh, it was CPP. Yes, yes.
Yeah, which does this. Okay, thank you.
Thank you very much.
I think there are no more questions. Let's thank the speaker again.
Thank you very much. Have a nice lunch.